All right, guys, so what we've talked about up until this point is we've talked about a bunch of different tests, how to tell whether or not something is convergent or divergent. And quite honestly, when you think about it, I mean, we've talked about the limit comparison test. We've talked about a direct comparison test. We talked about looking to see whether an alternating series is convergent. We've talked about absolute convergence. But when it really boils down to it, what we're trying to find out is my function getting small, and is it getting small quickly enough that I can tell whether or not it's convergent or not? And so in order to do this, like kind of simplify everything, what you can do is you can do what is known as the ratio test. Now, the ratio test is a way that you can find out whether or not a series is convergent by comparing two terms that are like way out there. Very, very, very large terms. Because if you're looking at two terms that are very, very large in the series, and I put one over the other, and the one on the bottom is bigger enough, if you will, than the one on the top, that it makes it be 0, then you can say that the series is growing small fast enough, okay? So here's basically what we use to do the ratio test. When we look at it, well, all we're doing is we're comparing two very large terms, and we're going to get a number when we compare those two large terms. We're going to make a ratio out of them. That's all this is saying right here. This is saying we're going to make two very large terms. They're consecutive terms. That's what that's saying right there. And then L just stands for the number we're going to get. Now, there's three different possibilities that you can get. You can get a number that is less than 1, or a number that's greater than 1, or a number that's equal to 1. And you're like, oh, well, no duh, that covers every single number that you could possibly get. But depending on what number you get, that tells you what you can, that basically tells you more or less what your series is going to be, whether it's going to be convergent or divergent. And this happens like 99% of the time. If it's convergent, you'll get this number will be less than 1. I would say most of the time that number is 0, but it's not all the time. Sometimes you just get a plain old number, but as long as it's less than 1, we say that it is convergent. If that number is greater than 1, then it's divergent. And basically what that's saying is that means the number on top is going to be bigger than the number on bottom when we're looking at the fraction that we're going to get. And if you get exactly 1, it's inconclusive. Now, usually if it's inconclusive, what you have to use instead, it doesn't happen very often, but what you have to use instead is you have to use the integral test to find out what the series is going to be, whether it's going to be convergent or divergent. And we'll look at one of those examples here in just a second. So let me show you what that means. Okay, so really all we're doing here is we're kind of, it doesn't seem like it necessarily, but we're kind of combining all of the tests together. And it says that on the screen here. We're checking to see if they're getting smaller. The one key to using the ratio test, and you'll see this as we start doing some examples here in just a second, there is a key. This is the test. If I were to tell you to use any of them, other than a geometric series, because usually you can recognize that you're looking at a geometric series pretty quickly, using the ratio test is always the easiest way to go about telling whether something is convergent or divergent, if only because when you use the ratio test, it's very clear. Like you just follow the same steps, and every single time you're going to get the correct answer. Okay? So the key to using the ratio test once you start using it is understanding that lots of stuff is going to cancel out. Like, for example, when I look, and I realize these are K's and not N's, and that's fine. Either way it works. But when I have this right here, where I've got 3 to the K on top and I've got 3 to the K plus 1 on the bottom, and I need to factor that, in reality, this is saying this. I've got 3 to the K over 3 to the K, and then I've got one more 3 on the bottom. In other words, the 3 to the K's cancel out, and I would have one additional 3 on the bottom, so this would factor down to 1/3. Understanding rules of exponents that you learned forever ago, and how, when I've got 3 to the K plus 1, really all we've got is 3 to the K and 3 to the first, and when we multiply those together, we add their exponents. This is a very, very, very important idea, because you're going to be doing a ton of this when we use the ratio test. Let me show you what I mean. Okay. Oh, one other thing I did forget. Another thing that shows up an awful lot in the ratio test is what is known as a factorial. Now, we might have talked about this before, but I want to make sure we talk about it again. A factorial is just a mathematician's way of multiplying a bunch of numbers and not actually writing it out. There is a pattern to the multiplication. Like if I have 7 factorial, that doesn't mean that I'm shouting 7. It means that I'm doing 7 times 6 times 5 times 4 times 3 times 2 times 1. In other words, you start at the number in front of the exclamation point and you multiply by all of the whole numbers underneath that number, okay? So if I were to factor this, what I really have here is 12 times 11 times 10 factorial over 10 factorial. So you'll notice that the 10 factorials cancel out, and all I'm left with is 12 times 11. Those two tips, when we're using the ratio test, actually make it a lot easier to actually follow through with the ratio test, because then you can say, all right, I kind of get what's going on in this problem. So let's say I wanted to test this one for convergence. Now, for the most part, I will say that you will see these letters as N, not K, but it's irrelevant what letter we use. What we do when we use the ratio test, and it looks really bad to start every single time. We do the limit as, usually it's N. I've got K written here, but it will normally be N. Approaches infinity of, then what we do is we look at 2 consecutive terms. The term, the infinite term that we look at, we just type in, or write down rather, exactly what we see for our series. In other words, I would take infinity and I'd plug that in for K, and that is one really big term. The next term that we use would be just the next term in the series, which would just mean I would add 1 to all of the n's or the k's that I'm using right here. Then what we do is we just do the absolute value of that, and I'm curious to know what number that gives me, if it's greater than 1, less than 1, or if it is exactly 1. So what we have to do first, if I'm going to let you know right now, if we plugged infinity in, you're going to get infinity over infinity. It's going to be the indeterminate form. You have to cancel stuff out before you go plugging infinity in for k, if you do at all, which in a lot of these problems you will not, and you'll see that in just a second. So I look at this and I'm like, okay, I have a fraction divided by a fraction. So I'm going to leave the top fraction as is. So I've got all of that. And then on the bottom fraction, I'm going to flip it upside down and you're going to multiply. So I've got 2k over negative 1 to the k times k. Now what we have to do, and this is where factoring becomes very important, you'll notice I have one more negative 1 on top than I do on bottom. So I'm left with a negative 1 on top after all of these cancel with all of those, and there's just one negative 1 left. On the bottom, there is one additional 2 than there is on the top. So I've got one extra 2 on the bottom, so that becomes 2 on the bottom. Then what I have, on the top I've got k plus 1, on the bottom I've got k. So that's multiplying, and then we've got this absolute value here. Notice now, if I do the limit as k approaches infinity, because we didn't evaluate the limit, what we're doing is I plug infinity in for k, and I've got the same power of k on top and bottom. What that means, because they're the same power, is this right here is going, we take their leading coefficients and we make a fraction out of them. That's going to be 1. So what I have here is the absolute value of 1/2 times 1, which gives me positive 1/2. Now, once I know what that number is, I say, okay, is that number bigger than 1, less than 1, or equal to 1? Going back, looking at your notes if you want to earlier, since that is less than 1, we know for a fact that this series that we are looking at is going to be convergent. Now again, there's an awful lot of factoring here, but as long as you can do the factoring, you can tell really quick whether or not not really quick, but fairly quick, whether or not a series is convergent or divergent. Let's take a look at another example. Okay, so I've got this one, and I want to, again, I would always say, if I'm looking for convergence, I automatically would go to the ratio test. So I take the limit as k approaches infinity of, remember the thing that goes on bottom is just our general term, if you will. Okay, so that right there is what goes on bottom. On the top, I've got, everywhere I see a k, I need to add 1. So I get negative 1 to the k plus 1 multiplied by k plus 1 factorial over e to the k plus 1. Now again, like I've said before, if we were to plug infinity in initially, we would get the indeterminate form. So immediately what we're going to do is we're going to try and factor this a different way. So I'm going to go, again, I'm dividing by a fraction, so I'm going to flip that fraction on the bottom upside down and multiply it to the top. And I know some people, when they do these problems, honestly, that's the first thing they do, because when we're using the ratio test, it's automatically That's what we do in all these problems. So if you want to write that, that's totally fine. This is still the absolute value. This is still the limit as k approaches infinity. So now I go factoring, okay? There's one more e to the bottom than e on the bottom than there is on the top. So those cancel with everything but one of those. So I've got an e on the bottom. There is one additional -1 on the top than there is on the bottom. So I've got a -1 on the top. Now realize here what we have is I've got k plus 1 factorial, and I've got k factorial on the bottom. If you think about this, this is the same as saying k plus 1 times k factorial. In other words, the k factorials can cancel out, and I'm just left with k plus 1. Now again, this is the limit as k approaches infinity. So I take the infinity and I plug it in, and what I get basically is negative infinity over e. I do the absolute value of that, and that just becomes infinity over e. I promise you, although I don't know exactly what that number is, I promise you it's bigger than 1. So since that is bigger than 1, we can say that we know that this series is divergent. Okay? And again, hopefully that kind of makes sense when we're using the ratio test. That should, again, hopefully makes a little bit more sense. Now, here's one, and again, I said we'd look at an example of one where you might not know exactly what's going on. It's 1 over k. So if I were to use the ratio test on this one, I'd go the limit as k approaches infinity of 1 over k plus 1 over 1 over k. So I'm using my ratio test. Okay, and this one's really easy. Nothing really factors. I get k over k plus 1. This is the limit as k approaches infinity. Now again, this is the harmonic series, so we know already that this one's divergent, but this is one of the few types of series that when I use the ratio test, I get exactly 1 for my limit as k approaches infinity. What that means is this is inconclusive. What we would have to do is go back and use the integral test on this particular series to find out that that is indeed a divergent series, because I know the integral from 1 to infinity of 1 over x is going to be equal to infinity. If that's the case, remember the integral test says if this is divergent, so too must the series be divergent. And a couple things have to be true. It has to be decreasing and positive the entire time on the interval in question. Okay, and this is indeed the case. Now, one thing, and it's not a super shortcut that you can use, but if you understand how functions grow, know that logarithmic functions grow the slowest, followed by, and we might have talked about this before, followed by polynomial functions. So x raised to any power, doesn't matter what the power is, those grow faster than logarithm functions, but they do grow slower than exponential functions. Anytime you have a number raised, I spelled exponential wrong. Exponential. That's right. Okay, so exponential functions grow faster than polynomial functions, and then, I don't know if this is important or not to you, but factorial functions actually I'm trying to spell and write at the same time. They grow faster than exponential functions. Now, the reason why that might help you a little bit is if I have a polynomial function, like not x to the third, if I have like 3 to the n power, and then I've got n factorial on the bottom, we can use the ratio test, but what you'll find every single time is because a factorial grows faster than an exponential, you will find out that all the time that that is going to be 0, if we just did the limit as n approaches 0, or infinity, excuse me, we would find that that's 0 right there, so we could use the limit comparison test, sort of. It's really just, if we use a really large number, we find that 0, you would know automatically that that one is going to be convergent. It's kind of a little help that you can use. I'd still recommend always using the ratio test on these problems, but it is something that if you're comparing two functions, you're trying to figure out whether it's convergent or divergent, it's something that you can use to at least get an idea as to what's happening. Now, of all the tests we have, and this is where we'll finish, but of all the tests we have, the ratio test is by far the most important because we use it in a different way in the next unit to help us understand some things that go on when it comes to what's called a power series, which is a different type of series that we'll talk about in the next unit. So hopefully that made sense with the ratio test. If you have any questions about how this works, please let me know.